Let's next see number 8. If L is a straight line in the plane, in the two-dimensional plane we have a straight line L. We have to describe the topologies it inherits, that means L inherits, as a subspace of RL times R, this Cartesian product, and also as a subspace of RL times RL. And it's also mentioned that in each case we get a familiar topology. So in the solution, what we first do, we first define two binary relations on the points of L depending on two cases. The first case is where L is non-vertical, that means L is not like this. It's either like this or this. That means it has some slope, whether positive or negative, but it's not vertical. Then for 2 points x times y and u times v in L, you understand that this is just x comma y, this is another notation. For two such points, we define x times y to be less than u times v. We also give it a name, say less than 1. If x is less than u, if the x coordinate of this point is less than the x coordinate of that other point. That is one relation. And next we consider the case where L is vertical, that means L is like this. So for any 2 points on L this time, the x coordinates are going to be the same, whatever that is, depending on what line we are considering, but the y coordinates will possibly differ. So for 2 such points, x times y and x times v in L, that's understood, I have not written that. This time we define x times y to be again less than x times v, but to distinguish this less than from this less than, we name it less than 2. If this time the y coordinate of this first point is less than the y coordinate of the second point, that is y is less than v. Oh, by the way, these ordinary less than that you see here, this is the ordinary order relation that we have in the set of real numbers. Now this is the thing, it can be proved that both of these binary relations are legitimate order relations on L. To better understand what's going on, let's look at this diagram. So you can see that here we have the first case where L is not vertical, but being not vertical, L can either have positive slope or negative slope. So there are two subcases. In this case, L has negative slope, and you can see 2 points on L. This one is the x times y and this one is u times v. Now by the definition of this ordered relation less than 1, this point will be less than this point if x is less than u as real numbers. That means if x lies to the left of u, which means that as we go along this line rightward, then we go down, then we get larger and larger points. This is the direction in which the inequality works. Inequality means this ordered relation works. As we go like this, we get larger and larger points. Whereas in this other case, other subcase actually, where the slope is positive, again the definition stays the same. So this time, if we go like this along L, then we get larger and larger points. The point here is that as we move rightward, we get larger and larger points. It depends on how L is tilted that we go down or up, which however has nothing to do with this ordered relation. For this ordered relation, having larger point means going to the right. And this is the other case where L is vertical. Say L is that straight line on which every point has x coordinate equal to x, which is some specific real number. Now on this line, if we consider 2 points like this, say x times y and x times v, here the order increases upwards. That means like this. The higher the y coordinate of the point is, the larger it is considered, or that's how this has been defined. So these are the order relations on L. Let's now consider L first as a subspace of RL times R with the subspace topology tau. We give it a name also. Let's first consider the case where L is non-vertical. That means L is either like this or this. Then its intersection, the intersection of L with a basis element, this closed open interval a comma b times the open interval c comma d, basis element of what? Basis element of this topology. This topology means, the topology that this space has, the product topology, that intersection is either empty or an interval of this type, closed L1 comma open L2, or an interval of this type, open L1 comma open L2, where in this ordered set L comma that less than 1. And that is why tau is similar to the lower limit topology on R. But what is going on here? We have to understand two things. How exactly this is true, that is one thing. And the other thing is, what does this last line mean? What does it mean for tau to be similar to the lower limit topology of R? Note one more thing. Oh, and by the way, why did we consider this intersection in the first place? That is because you recall that the product topology that this space has is by definition generated by a basis where the elements look like this. Why? Because from a previous result we know that if this space has a basis and this space also has a basis, and you take products of basis elements from those two bases, you take basis elements and take their products like this, then the collection of all such products forms a basis for the product topology on this, and that is the topology that this product space has. And RL has a basis where the elements look like this, closed open intervals, and our usual R of course has a basis where the open sets, the basis elements are open intervals. So sets like this form a basis for the product topology on this space, and that is why by the definition of subspace topology, if we take intersections of these basis elements of the product topology with L, then also we get a collection of sets that will be a basis for the subspace topology tau. So if we can figure out how these intersections look, then we can have an idea of what type of topology tau is. That is why we did this. So let's now understand this and this. So let's consider this basis element for the product topology, closed open interval a comma b times open interval c comma d. We can draw its figure and it looks like this. What are we looking at here? Here we are looking at a rectangular region. When you think of this geometrically, this is what you get. This is the point A comma C, this is the point A comma D, this is the point B comma C, and this is B comma D. Alright. Why did I draw this line normally whereas these are dashed lines? That is because in this set, when you consider it geometrically, no point on these sides are included. Okay, they are not included. However, the points on this side are included. Why? That is because of this closed end. And there also there is something that you should note very carefully. These endpoints A comma C and this endpoint A comma D themselves are not included. Why? That is because you just look at the set. Do you have the point A comma C in this set? No. The first coordinate A is inside in the first set, but the second coordinate C is not in this interval. So that means geometrically the region that we are looking at consists of all points that lie in this interior of the rectangle, that's fine, along with points on this line segment, but without these endpoints. So that's what this basis element looks geometrically. And now we come to our line. Our line is given to be non-vertical. So it may have negative slope or positive slope. And also it may be situated anywhere with respect to this basis element. So now we will look at the possible cases of how L can or it may not intersect this basis element. These are the possibilities for L. L may be like this, or L may lie on that side also, and that also L may be tilted in any way. Just the thing here is that L is negatively tilted in the sense that L has negative slope. Okay, L may be steep or it may not be that steep, anything can happen, but say L does not intersect this at all, then of course the intersection is empty. Next, if L intersects this region like this, that it passes through those edges which are not included in this set, in this basis set, then what is the intersection? The intersection is this line segment, which is a part of L without its endpoints, which say we are calling L1 and L2. Now you think of the ordered relation that L has. According to that ordered relation, this is the direction in which points increase. So that means in this ordered set, this is an open interval L1, L2. So that's why we wrote that here, there I mean. And in this third case, L intersects this basis element like this. L intersects this edge which is not there, but L intersects that edge which is there. So that means in this case, that corresponding interval will be the closed open interval L1, L2. So that's how we have this type of intersection as well. And you can convince yourself that if L is negatively tilted like this, then these are the three possibilities. Similarly, if you have positively tilted L also, these will be the three possibilities. Now next we come to the meaning of that last line. In what sense are we saying that this subspace topology is similar to the lower limit topology on R? That sense at this moment is still not there with us. It will come when we learn about homeomorphism. Just like you have the notion of isomorphism between two algebraic structures, say of the same type, say two isomorphic groups or two isomorphic rings, vector spaces, fields. Like that, you also have two topological spaces which are topologically the same. Okay, it's just that they look different. One can be molded into the other by topological transformations, which are actually continuous functions that are continuous both ways. That is, the function is continuous and its inverse exists, and that is also continuous. But because we still don't really know about homeomorphisms, so right now we just take this somewhat vague view that because this L looks like just R, our ordinary real line, but only tilted like this, and in such a way that this is, say, the positive direction of the x-axis when you think of R as the x-axis, then the topology that you are getting here as the subspace topology, whose basis elements are just the basis elements that we have for the lower limit topology on R. That is why the topology that you will get here on L is exactly like the lower limit topology on R. The technical statement would be this, that L is homeomorphic to the space RL, that is R with the lower limit topology. But right now we don't really know what that means. In that sense, I wrote similar within quotes, but it's the familiar topology. Now that you understand what's going on, we can go ahead with this next case and understand it more quickly. Next, let L be vertical. Okay, we are still with the product space RL times R, but this is the other case. In that case itself, within that, L can be vertical as well. So now L is neither like this nor like this, but L is like this. Then the above intersection, that means that intersection of L with this, is either empty or an interval of the type, this time only open interval, L1, L2, in this other ordered set. Don't forget that when L is vertical, we defined a different order relation on L, but still that is an order relation. In that order relation, we can consider this open interval. And I leave it to you to figure out why that is the case. You think of sliding a vertical line, making it meet this region, and then you try to think of the possible intersections. You will see that in this case, you will never get a closed open interval. That type of situation won't arise in this vertical case. But then, this time the subspace topology is similar to the ordinary standard topology on R because of this type of interval. And then we go to case 2 in the exercise. That means this time we are considering L as a subspace of this other product space, RL times RL, where both the factor spaces are real lines with the lower limit topology. With the subspace topology, which this time we name U, say. This time, if L has non-negative or infinite slope, that means if L is tilted like this, non-negative means the slope can be 0 also, that means L can be horizontal also. Either like this or like this or like this. Having infinite slope means being vertical. If that's the case, then U is similar to the lower limit topology on R. I need to draw another diagram because this case is different. Let's first see the typical basis element for the topology on RL times RL, which is a Cartesian product of half open intervals like this. This time both are closed open. Closed A, open B times closed C, open D. So the rectangular region this time will be like this, where of course we have everything that's inside the rectangle, but this time this lower edge and left edge are included. However, the top edge and right edge are not included because of this different types of endpoints. Okay, and note carefully that the point A, D, that means this corner is not included. This corner is also not included. B, C is also not included. And of course, this corner is also not included, B, D. However, A, C, this corner point is there in the basis set. So what did we say here? That if our line L has non-negative or infinite slope, then U is similar to the lower limit topology on R. So here you are looking at some possibilities for a line having positive slope, right? So it may not intersect this basis element. In that case, the intersection is empty. If, however, it is intersecting the basis element like this, no matter how you slide the line and make it intersect this region, you are getting closed open intervals. Where? In L. Okay, with respect to the order relation less than 1. You remember, in less than 1, things increase rightward. So as we move rightward along the line, we also have to go up, but things increase in that direction. So the left end which is closed, it matches with what we have in lower limit topology. Also you see one line that is horizontal. If you slide any horizontal line like this up and down and make it intersect this region, here also you will get closed open intersections. So that is why in this case it's the lower limit topology. Oh, there is one more thing, no? Vertical. There also you check, you will get this type of intersection. So that is why we have this. And finally we have only one more case for us to see, which is when L has negative slope. That means L is now like this. Now we choose any point A times B in L, just any point. And then we choose real numbers C and D, which are respectively greater than A and B, that we can always do. And then we consider this singleton set consisting of only that point. It turns out that this equals the intersection of L with this basis element, closed open interval A comma C times closed open interval B comma D. So what do we find here? Here we found that every singleton set, every one point set in L is open in the subspace topology U. So in this case the subspace topology U is just the discrete topology on L. And to also better see what's going on, let's draw another diagram. So in this case this is the situation. This is our L and this is the point A times B. Alright. So then what did we do? We chose a real number C greater than A. Okay, so that real number is say C here, somewhere on the real line. Real line means the x-axis. And we also chose a real number D which is greater than B on the y-axis, wherever that is. And then we considered this basis element, A comma C times B comma D, A comma C times B comma D. So we are getting this rectangular region where you know by now that these two sides are included without these two endpoints, and also these two sides are not included. All the interior points are included, and along with these two sides, this corner point is also included, and that's a very important thing right now, because that corner point is our A times B. And you can clearly see that the intersection of L with this is just that one corner point. So in this case, like that, these boxes come and create singleton open sets on L, thus giving us the discrete topology as the subspace topology that L inherits as a subspace of RL times RL. So do you see that how things drastically change if L goes from this type to this type? Okay, the topology changes entirely. And the video also ends here. Next week we will solve exercise 10, which is, I think, yes, it's the last one in this section. And after that we can go to the next section, which is about closed sets, closures of sets, those things.